All right, so this video is on Chapter 5, Evolutionary Psychology, but I actually broke up Chapter 5 into two parts. The first part is where I'm going to go over some of the challenges to the conditioning models. Basically, what what research has been done that maybe suggests that classical conditioning and operant conditioning aren't entirely accurate and capturing all of human behavior. The next video is going to talk more about evolutionary psychology, and so I'll unpack that. But again, right now, what I want to do is kind of look at how do we think about the conditioning models, classical conditioning and operant conditioning. Now, of course, one part of the criticism of these models is that they're reductionistic, and that absolutely stands because they're reducing human behavior to these, well, human behavior, animal behavior to these very small elements, right? What can you scientifically test? You cannot test something as complex as how people have a dynamic relationship. You have to test actually, oh, well, why are they emotionally reacting like this? And it's very specific. But that's not what this section's about. Instead, it's actually about some of the research that's been done and how some components of the research has challenged some of the basic models. Okay, now it's important to kind of go back and think about what are the assumptions of classical conditioning and operant conditioning. So for classical conditioning, there's an assumption that everything that is repeatedly paired with an unconditioned stimulus will eventually elicit a response. So if you take something, a stimulus that you have a natural reaction to, a reflex, automatic response to, if you take that and pair up another stimuli with it, it's always and reliably going to elicit a response for whatever you're pairing with it, the conditioned stimulus. It also assumes that you have to have repeated pairing. It's not going to happen in a single shot. And finally, the CS and US must be contiguous. They must occur together at the same time. And so we're going to look at whether those assumptions are always true. And then the operant conditioning assumptions is that learning only occurs when a consequence is present. So if you learn in the absence of a consequence, and of course with barring classical conditioning, that would not be a part of this model. So the basic model across classical and operant conditioning is that behaviors are conditioned by what occurs immediately prior and immediately after our behaviors, right? So you have stimulus, response, consequence. Again, just iron that into your brain. Stimulus, response, consequence. So stimulus response has to do with classical conditioning, and response consequence has to do with operant conditioning predominantly. So the research has actually shown that our behavior changes very little from consequences that occur more than just 10 seconds after the behavior. So it's immediately after our behaviors that the operant conditioning is really at play. Now, that is interesting because there is a behavior that can be exhibited that's actually pretty important for survival, but that actually doesn't seem to align with that finding, right? The immediacy of the consequence. And that is taste aversion. Now, I imagine that some of you watching this have developed some sort of a taste aversion. Sometimes people develop an aversion to oysters or sushi or things that are that they actually get food poisoning or something happens. And what can happen is humans and animals can develop strong aversions. They'll basically become nauseous even at the thought of eating something, because in the past that food led to sickness. Now, at first glance, classical conditioning seems to provide a good explanation of it, right? You pair up the the food with some sort of virus or some sort of bacteria that, and the bacteria or virus is a cause of getting sick, nauseous, food poisoning. Now you've paired up the food with the virus, and so the food, all the conditions of it, the taste, smell, just the sight, all of those get associated with the virus, and therefore you have the nauseous reaction. Okay, so at first glance it seems like a good explanation, but it doesn't really pan out so well. So conditioning doesn't explain. The problem with it is that so the problems with the classical conditioning explanations is that, first off, it occurs in one trial. So food aversion can occur in a single episode. You have one bad oyster and you're forever ruined to oysters. Now, so that's a problem. And then the second problem is that there's often a delay between ingestion and sickness, right? You don't immediately feel sick in the most part, right? So you can eat something and feel fine for a few hours, and then after a few hours, 8 hours, 12 hours, and you can actually develop that food poisoning, and yet you can still go back and connect it to the food that you ate and say, oh, that's what happened, and you develop an aversion to that food. In fact, one study found that taste aversion can occur when sickness occurs 32 days after ingestion. And that just blew my mind. So a person can get sick 32 days after they ingested something, and they could still develop a taste aversion to that thing. And then the third one is that there's a selectivity in taste aversion learning. So there's particular foods that we're more likely to develop aversion to. And well, actually, what that means, sorry, it's selective, right? So we're associating food with the nauseous response. We don't associate the fork or the restaurant or all the other, the people that are around you. It's very specific that it's always the food that you develop the aversion to. Okay, so this can actually be flipped around. So they've shown that they can develop taste aversion to ice cream. So the people undergoing chemotherapy often develop nausea. And now, one of the things that you might think for that last, for taste aversion is maybe it's all cognitive. Maybe we're connecting the dots and it's all like, oh, I know that taco is what gave me food poisoning, and say, oh, well, that's why I'm averse to it. It's all cognitive. But they actually showed that you can develop a taste aversion even though you know the food that you ate wasn't the cause. So they did this with ice cream, and the patients getting chemotherapy knew that it was the chemotherapy that made them nauseous, but the beliefs didn't seem to have an effect. And so taste aversions will only be associated with taste, not with lights or tones or with the silverware you ate. That's what I said in the last slide. Now, clinically, what do you do with this? So there's some implications. They've shown that if you use rapid smoking, and maybe you've seen this in the TVs and movies or something, but this actually can work. If you get someone to smoke very quickly, it's shown to, well, which leads to nausea, right? If you smoke a whole pack of cigarettes in a couple hours, you're gonna get sick. It's shown to be effective actually at decreasing cigarette smoking, right? Because that person's gonna have a memory of the nausea and associate with smoking, and that seems to work well with people that are a little bit newer to smoking. Another example is alcohol aversion therapy. There's actually a medication called antabuse. It's a FDA-approved medication to help people with alcohol use disorder or alcoholism. And what it does is when they take the medication, it will make them ill when they drink even a few drops of beer. So it's actually taking advantage of, again, this taste aversion, and it makes people averse to alcohol, and so it can help some people in their recovery, because they if they do take a drink, if they do have a slip, then they can have a very negative reaction, and as a result, the next time they're thinking of drinking a beer or drinking alcohol, they might actually get a little bit of a physiological response to it. Another challenge to classical conditioning, so I guess this is moving to another topic, is that latent inhibition can actually play a part. So again, one assumption of classical conditioning let's see here. So pre-exposure to a stimulus lessens the likelihood that associations will later form between the stimulus and negative outcomes. So if you brought a person to the medical office where they would receive chemo, had them sit in the office where it would be administered, then but then they didn't receive the chemotherapy at that time, what you can actually find is that they have less of a reaction to just walking into the medical office, and which is often a problem for people receiving chemotherapy. They go there, it's the first time they go there, they get chemotherapy, and then the next time they go there, they got so nauseous the last time that they're like, I just can't walk in, it's too much for me. And so that could sometimes be a barrier. But you can take advantage to latent inhibition by having them go visit the medical office a couple of times, pre-expose them, right? So they see the office, they're associated with it, but they don't have a negative reaction. And then, that second, third, fourth time where they go and they do receive chemo, they have less of a aversive reaction to the office. So again, this is a challenge to operant conditioning. There's an assumption that nothing is learned if no consequence is present. So if that's true, why would previous exposure change the response if nothing was learned previously? So this is kind of an interesting case where maybe we are learning something. We're learning that nothing happens, which is kind of an interesting idea. So another example of this, you've probably heard of the idea of being friend zoned. I get a kick out of this example. You might typically respond to someone who starts to flirt with you and tries to get you to like them. That, I think that's just human nature. But if you originally are friends with a person and then they start to flirt with you, you're probably more likely to friend zone them, because you already have this learned association that, oh wow, this is my friend. You already have an association with them at a certain level, and you might not respond when they actually are flirting with you. And I don't know, I get a kick out of that example. Okay, and a third example of this is blocking. And blocking is really interesting. In fact, they've done a lot of research on this finding. Okay, so, but it's a little complicated. Let me try to unpack it a little bit for you. Okay, so let's say you randomly assign a group of rats, so that one group of rats basically gets a normal conditioning response, and they are conditioned to associate a noise and a light with shock. So in that group, they have a buzzer go off and a light go off at the same, and a light turn on at the same time. So the buzzer and the light comes on, and then a shock comes a half second later. Okay, so that's the control group. That's the normal classical conditioning. That's pretty standard. And then the B group, it's the same thing. So they do they do noise and light with a shock, but before they do that conditioning, they first get a pre-training, and they train them with a noise, and then a shock, and then they do the conditioning. Okay, so the conditioning with the noise and the light with a shock. What they found is that the first group, if you only show the light, well, they would normally have noise and light. If you only show the light, the rats would freeze. They'd have a lot of fear, right? They'd be like, okay, well, the noise isn't playing, but that light's on. I'm scared. I'm going to get shocked. But the other group, okay, in that other group, there was a initial conditioning phase where they had a noise and a shock, but there was no light involved. But then they were also conditioned noise and a light, and that led to shock. So for this one, it was interesting because in that condition, when they showed the light alone, there was no fear. They would just go on as if nothing is occurring. All right, so the idea here is the light got blocked. Okay, again, classical conditioning assumes you just need to present the stimuli together, right? And so the stimuli in this case is the noise and the light. Those are both the neutral stimuli. And then you pair them with a shock. And the shock is, of course, the unconditioned stimulus. And so you pair those two with the shock. Normally, if you only present one of the two stimuli, you're still going to get that response. Maybe not so strong, but you still get the response. But if you first associate noise, and that predicts a shock, when you add the noise and then the light, when you add the light doesn't seem to be learned. So the light doesn't become classically conditioned to elicit that fear response. Okay, so a conditioned stimulus that is repeatedly paired with an unconditioned stimulus can sometimes not elicit a conditioned response. Well, what's happening? How do you explain this? And let me say the last things there. This can occur for both animals and for humans, and so it's not just like is this conscious? No, it doesn't matter. It also occurs when another stimulus was learned as a response with a signal. So this has puzzled a lot of researchers, but a pair of researchers, Rescorla and Wagner, came up with a model to help explain this. It's a prediction model. So it argues that classical conditioning is not just about, transferring a reflex to a new stimulus. It's about predicting what's going to happen. So organisms learn to predict the occurrence of the US by using a CS. All right, let me explain what that means. They learn to predict the shock by using the noise. And you could think of the prediction of the US, you could think of it as being 0 to 100%. So it's 0% at first. Okay, so if you present the CS, the noise, at first, there's no prediction of a shock coming, right? Well, the first time you do a noise and then a shock, well, the animal learns, and the next time around, maybe it's a 10%. There's a little bit of a response to the noise, and then you do it again and again and again and again. So after some point, the CS-US connection is fully learned, and the organism reaches 100% accuracy in prediction. Well, once you reach 100% accuracy, it's kind of interesting. You ignore or block other sources of prediction. So once you predict noise and then the shock, noise, shock, noise, shock, noise, shock, then if you add in noise and light shock, noise and light shock, noise and light shock, the organism effectively ignores the light. They block the light. It doesn't factor into their prediction. So then if you only turn on the light and there's no noise, there's zero response to it. There's zero fear to it. So here is how we can sort of think about it. Traditionally, it says a response is simply transferred from a US to a CS. But Rescorla argues that classical conditioning occurs only when the organism is surprised. And I love this. It's an interesting way of talking about classical conditioning because it usually sounds so boring. It's about eliminating surprise. We're always trying to understand our environment. We're always trying to understand what's about to occur. And classical conditioning is our way of achieving that. So we could be surprised in one of two ways. We could be surprised when something occurs that was not predicted, and that's when we acquire a classical condition response. And then we could also be surprised when we make a prediction, but it doesn't actually come true. It doesn't occur. So for Pavlov, the bell before the food. All right. So the bell is the at first there's a bell, and then the dog is surprised because the food is brought out. All right. That's a condition where the dog is learning. Extinction is also a process of learning. When happens when the bell rings, the dog expects the food to come out, but is surprised to find the food doesn't come. And that's when extinction occurs. So it's like this up and down of making these predictions, 0% to 100%. And so if you're learning, you're moving up to predict what's going to happen next, and you're trying to get to 100% accuracy. And if you're being extinguished, you're getting to 0% accuracy. You're, I won't say unlearning, you're extinguishing the response. So Rescorla had this quote. I think it's helpful to think about it. Pavlovian conditioning is not it's not a stupid process by which the organism willy-nilly forms associations between two objects that happen to occur. All right, that's usually how we learn about classical conditioning. Rather, the organism is better seen as an information seeker using logical and perceptual relations among events, along with its own preconceptions, to form a sophisticated representation of the world. Again, I love this because classical conditioning, it sounds like, oh, we're just brainless machines that are, oh, got to connect CS and US, and it sounds so dull, to be honest. But this is suggesting we're trying to predict what's going to happen next, right? I mentioned before that with addiction, when someone is using in a hotel room, their body isn't predicting the drug is coming, and so when they use their normal dose, there's surprise, right? They're going to get overwhelmed. Their body isn't ready for the same dose that they normally have, so their conditioned response isn't kicked in, and as a result, they can overdose because their body's not ready. And that's not just some dull, basic mechanical process. It's about like cognitively trying to understand the world and predict what's going to happen. So I love framing classical conditioning as surprise. It's reducing surprise in the world. So to kind of review, the research findings show that with blocking, not everything that occurs with the US will elicit a CR. With taste aversion, it found that classical conditioning can occur in one trial with several hours in between and be selective to one sensory input, taste. And with latent inhibition, operant conditioning can be affected by previous exposure, even if no consequences were present. So all of those are challenges to the conditioning paradigm. So I like to think of classical conditioning as a process of learning what goes with what. The bell goes with the food. For the eye blink conditioning, the rabbits in the eye blink conditioning, you're connecting generally it was a light with the puff of air. With quail sex conditioning, kind of same idea. The light is associated with the availability of a female. And that's really what it's all about. But of course, this assumes a mental life. It's saying that when we're learning, it's not, you cannot just simply do it as if you can study the environment and the behavior. You have to appreciate that there's a mental life going on. And it's interesting because it even suggests, well, rats are reasoning about cause and effect at some level. Okay, so that's it for this first part. Next part, we'll talk about evolutionary psychology, but I wanted to cover this. So, all right, I'll end there.